Welcome to this fourth installment of this series of videos on incremental view maintenance. In this video I will talk about the DBToaster Aggregate calculus, which is a query language which will allow us to do recursive incremental view maintenance. If you recall from the previous video, we set a set of two requirements for a query language. The first being that the query language must be closed under ticking deltas. That means for every query, the delta must be also a query of this language. Furthermore, we require that there is some k for every query, such that the delta to the kth delta of the query is 0. Now, if these two conditions hold, then we can do recursive incremental view maintenance exactly in the way we described and discussed in the last video. So, in this video, I'm going to discuss such a query language that satisfies these two conditions. And I will basically create a useful query language that is as close as possible to the ring language. That means we've got generalized multiset relations as the values of the language and the operations plus and multiplication to do useful expressions. Well, in general, this generalizes the relational union and the natural join, but that by itself is probably not yet a strong enough query language. If you think about relational algebra, what we would at least need would be, in addition, projection and selection. In practice, we would also like to do powerful aggregations, and in fact, in a bag-like language, projections and aggregations are very closely related, and we will actually have one operations for both. Furthermore, we might want to have things like a relational difference operation, and actually the relational difference operation doesn't exist explicitly in this language, but it is expressible using nested conditions and aggregation. On a high level, the syntax of our language, the aggregation calculus, is shown as follows in this grammar. So we have basically two ring operations, plus and multiplications. Furthermore, we've got minus, which is basically a special case of plus, or we could think of it as a plus of a term multiplied with minus 1. So we will change all the multiplicities to the negative. We have a way of expressing minus 1, which is actually expressed and captured by this f. We will talk about what f is later. Furthermore, we've got an aggregate sum operation. I consider this not really a true extension, at least not causing problems in our language of rings, because this sum operation is really just a repeated application of the plus operation. With this sum operation, we can do two things. We can compute aggregate sums. By the way, that way we will also be able to count. Given that and basic arithmetic, we will also be able to compute ratios of sums and counts, which will be averages, and so on. We will also be able to use this as a projection, a duplicate preserving projection. So in general, this sum can take group by values. I didn't show this explicitly, but you can say sum subscript AB, and that would basically group by these columns. That way we can do a sum group by as an SQL. And that we will also do a projection, because it will project away all other columns except for those group by columns. Also in bag relational algebra, the idea of projection is that it's usually by default duplicate preserving. So we can actually basically count and do aggregate count operations with group bys in relational algebra with bag semantics using just a projection operation. I use the sum syntax rather than a projection syntax here because I want to stay in line with this idea of rings that have plus and multiplication, as it's really only true operations. Now, we've got a number of ring elements. The ring elements are the relations, the generalized multiset relations, R of x, and then we will have variables, and these variables can basically refer to columns inside our relations. As I said before, generalized multiset relations in general don't have the same columns and same fields in all tuples. In this particular context, I will actually assume that we will have types, and our relations will all have all tuples of a relation will have the same schema. Remember, we introduced this just to be able to kind of use the framework of rings, but it is no loss of it is no problem to then use the rings in a more restricted fashion. Use them only in such a way that actually we can type the relations and use plus in a typed way. Furthermore, we've got functions f, which will be either constants, that means nullary functions, constant values such as -1 or 5, or they can be built-in functions such as division of integers or something like that. And finally, we've got conditionals. And conditionals will compare a query evaluating to a single value. That means maybe a nullary tuple with a multiplicity. We will take the multiplicity and compare it against 0 with equals, less than, greater than, and such. This is the data. So importantly again, we can think of, without true loss of generality, of saying, well, there is ring elements, values, and there's operations, and our operations are really just plus and multiplication. The only exception are these conditionals, and we'll have to deal with those. Now, there are ring elements which are not relations. We've got relations, well, they are relations. We will have variables, and we can think of those as, and that's the same thing for constants, we can think of those as taking a nullary tuple to a multiplicity. The multiplicity is the value of the variable. Same for constants. And ultimately also same for functions. However, functions take arguments. And we will have to deal with this. The other thing is that conditionals, in general, we cannot really think of as relations. They will not be finitary. If you, for example, test x minus y greater than 0, which is the same as x greater than y, as a condition, you can think of this as a relation in variables x and y, but which may have a multiplicity greater than 0, or different from 0, for an infinite number of values. And we will have to deal with this. And we will have to do something similar to what people have done in the theory of relational calculus, so-called range restrictions. For that, we will introduce a new notion of so-called avalanche rings. And we will generalize our multiset relations, our generalized multiset relations, to something even more general called parameterized multiset relations. So remember, a generalized multiset relation was a function from tuples to multiplicities. It was conceptually defined on all possible tuples, an infinite set of tuples, but only a finite number of tuples were allowed to have a multiplicity different from 0. So we could tabularize this and store them explicitly. This was not a program that would compute things, but we could store them explicitly as data in a database, these functions, because they were finitary, only a finite number of tuples had non-zero multiplicities. Now we're going to actually truly generalize these GMRs to functions. They will take parameters, and only if you are given parameters, then we will be able to evaluate these GMRs. So in that sense, they would be second-order functions. We will be able to use these GMRs to model binding passing in our query calculus. So that's similar to relational calculus. In relational calculus, I can say something like r of x, y, and x less than y. And this and x less than y is what corresponds to a selection in relational algebra. Now, if I would like to express every atomic formula of relational calculus and think of it as a relation, then I have a problem, because r of x, y is a relation, but x less than y I can think of as a relation between x and y as a binary relation, but it will have, in general, an infinite number of tuples inside. Now, in relational calculus, this is solved by saying, well, I'm allowed to use x less than y, but I'm only allowed to use it if left of it I've got a relation somewhere, or a query that evaluates the relation, a query that is safe. And I can combine it with AND. I'm actually not allowed to combine it with OR. That way, I also know where the values for x and y come from. And x less than y is only a constraint on the tuples that come from rxy. And it's not anymore an infinite relation. That means we protect every query result by always guarding any infinite relation with a finite relation. Although x less than y is an infinite relation, it is ANDed, is intersected with a finite relation rxy. We're going to do the same thing. And that way, and we conceptually do this by passing bindings from the left to the right. We're passing values that for x and y that are safe, they come from a finite domain, to the right, and then constrain these values further using a constraint like x less than y, and then can pass them further. And that way we can basically chain together complex queries that again behave the way we want it. So this kind of avalanche of values, like flowing to the right, is something that we want to model. And we have this notion of avalanche ring that actually guarantees the property that we had before that we still want to preserve for such a generalization of generalized multiset relations. This is all a bit complicated, but the important thing is we are able to build a ring that still has all the important properties. So how do we do this? Well, the definition is actually given here. So I generalize plus and multiplication here, and it has all the important properties in the following sense. It is a ring. Multiplication in general is not commutative anymore because we're passing things from the left to right, but otherwise it has all the same properties. It looks more complicated because it has this way of not just taking a tuple and computing for each tuple a multiplicity, but taking also some bindings. And the bindings are truly input. The tuples, these variables here, we will only have for a finite number of tuples some non-zero multiplicity. But we will only be able to evaluate, this relation, this generalized multiset relation, x goes to some multiplicity, given some bindings. And for different bindings, there might be a different domain for x. That's the way how we solve basically this infinity problem. Now, this looks a bit complicated, but ultimately it's just a very straightforward and very natural generalization of the original convolution product, where we have a way of taking bindings and passing them to functions and passing them on. So the results of one function on the left-hand side extends the bindings, and they are all passed together to the right. So if I've got a chain of multiplications, I can pass valuations to the right and use them to constrain conditionals. So in the particular case that I have no bindings as input, an empty tuple of bindings, and the bindings coming from the left are not used somewhere. That means I wouldn't use y. G of y z does not depend on y. It depends only on z. Then actually this definition, both for plus and multiplication, specialized to exactly the definition we had before, which was the original ring for GMRs. So, and in that case, it is also commutative. So that's exactly what we wanted, and it solves our problem. We have basically made an algebraic version of range restrictions and relational calculus. Now, for our language now, we can very immediately define deltas for all cases. Actually, I'm not showing the case for built-in functions and constants, because for that, the deltas are just 0. Actually, I show them down there, but not for constants. But we have already seen that deltas for plus and multiplication is exactly what we had before, given by the basic laws of rings, and they hold in our avalanche rings as well. Sum is just a repeated plus, so basically our rule for plus is just applied here multiple times. We can think of the delta of a relation being just what is given, this delta. I can enumerate this explicitly by constraints if I like to. The delta of some relation applied to different relations is empty. Yeah? And the delta of constants and functions is also 0. So the only thing that is complicated is the delta of a conditional. And in the worst case, there's really nothing smart we can do. The delta of a conditional is actually not easier than recomputing the conditional. So we can only say, well, the delta of a conditional is the new value minus the old value. And that is, of course, not very desirable, and we're going to try to avoid computing this. However, there is a special case, the special case that in this alpha here, no relation occurs at all. So we can only use variables passed from the left, bindings, etc., and compute with those, plus multiplication, constants, built-in functions, and stuff like that. All this can be used, but no relations. In that case, a delta is always 0. So it's a very simple case. In the most general case, which would basically mean nested queries inside conditions, inside where clauses, taking SQL terminology, we have nothing better than basically recomputing. And that's ugly, and we're trying to avoid this. Now, we can also define degrees for our language. It is done exactly, the way it's done for polynomials. The degree of a product is the sum of the degrees of the constituents, of the factors. The degree of a sum is the maximum of the degrees of the constituents. The degree of everything else is basically, well, degree of a minus is just the base term, for a sum as well. Of a conditional, it's the degree of what is in the condition. And finally, the degree of a relation is 1. Because these relations The changeable relations are exactly the variables of a polynomial. So this is exactly the definition of degrees of polynomials. We have also an additional definition that we say a condition is simple, yeah, if no relation occurs in it. In that case, the delta of the condition is actually 0. In that case, in case that you have only simple conditions, right? In that case, the degree of the condition is also 0 here. We have a theorem that for any term, for any expression, any query of our language that uses only simple conditions, the degree of the delta is one less than the degree of the query, unless the degree of the query is already 0. So that's exactly the theorem that we wanted. So on the last 2 slides, I've shown a way of doing deltas for every construct in our query language. And on this slide, I've given a notion of degree such that degrees are strictly decreasing. Deltas are always easier. And these were the 2 conditions required for being able to do recursive incremental view maintenance the way we described in the previous video. So we have a solution. Let's do an example. So I've written here a simple SQL query, and it is along the lines of the so-called DBCH queries schema. So we have orders and we have items inside the orders. Orders have been made by some customer that uses a certain exchange rate against our own calculation currency. So that's exchange rate. And each list item, each line item in the order has a price. So if I would like to know the total sales across all orders, I could use this query. I could join the orders and the line items with order key. It's a foreign key relationship. And then sum the products of the exchange rates with the prices for each of these line items. So that is a reasonable query. It's an aggregate query. In our calculus, we can express this by the following term. So observe that order and line items are relations, and the multiplication is the natural join on them. I can also use variables coming from those relations. That means columns, P and exchange rate from order and line item, and just multiply those in. What does this mean? I haven't given the semantics explicitly, but the semantics of a variable is basically constructing a ring element which maps the empty tuple to multiplicity variable value and all other tuples to 0. So I can just multiply these in. So naturally joining this any relation with such a variable multiplies all the non-zero multiplicities of the tuples of the relation with the variable value. And we do this, we multiply the variable value into the multiplicity for product and for exchange rate. That way, I multiply the multiplicities, which are either 1 or 0 initially, because these are base relations, classical relations, with the product that we actually wanted to compute. And now I project away all the columns. I collapse all these values, sum up the multiplicities, and the multiplicities are actually the aggregate value. That's exactly what I wanted to do. So this is the query result. I've not shown in detail the semantics of the queries, but for this I will refer to the literature. There is a number of papers on these slides in which you can actually find the exact definitions of all these, the semantics of all these operations. Now, the important thing is the degree of this expression is 2. Why is it? Because we have just multiplications here. The degree of this product of 4 things is the sum of the degrees of these 4 terms. Well, the degree of the relations is 1, 1 plus 1 plus 0 plus 0, because the variables have degree 0. Now, and the degree of the sum is just the degree of what is inside. So the degree of this overall aggregate query is 2. I can also compute the delta, let's say for orders. As I insert a single tuple order key exchange rate into orders, the delta is the following. Well, we had the definition before. It is going to be the delta. So we've got 4 terms in this product here, and all but the one which is order here will have delta 0. So only one term survives this big product definition here. That we would have 3 terms if we multiply 2 things, but we will actually multiply in 3 steps 4 different things together, 4 different factors together. So actually, if I would actually try to express this using distributivity, I would get quite a long collection of factors. We're not going to do this. The fact is that all but one of these terms here have delta 0. So the delta of this product of 4 terms is actually delta O times line items times P times exchange rate. Now, what is the delta of O? It is actually exactly this insertion of this new tuple. Now, I can do this. I can basically pass the bindings, and exchange rate, which was a column of the relation order, now becomes this particular variable, this particular parameter, lowercase exchange rate. And otherwise, I will have to fill in a constraint, because the natural join of order and line item on order key will basically put in my constraint line item order key is the order key coming as a parameter from, so to say, the on insert trigger. So, so this is our delta, and the degree of the delta is 1, because there's only one relation left in it. So finally, again, I'll point to these 2 papers that you can find on the web, which give detailed semantics definitions and lots more examples.